Hi, I'm going to be taking you through a bit of nodal analysis. It's one of the core concepts of any intro to electrical course, and it's usually worth like quite a bit of marks. Um, so it's good to know it, and it's also introduced in later courses in just showing you how other things work. It's one of the most common analysis techniques you're going to use in circuits, so it's very good to get it down. So I'm going to start really simple. Here's a circuit with just one node. And it's really just going to be about understanding what we actually do when we're doing a nodal analysis. I'm not going to assume that you know very much. All you need to know is Ohm's law, which is V equals IR, and you're going to need to know KCL, which is Kirchhoff's current law. So our node is that red dot up the top of the circuit there. And we want to find the voltage at that node. This is what nodal analysis is. So what we need to remember is that a voltage is a potential difference between 2 points. So this has confused me at first. You might ask then, how does a node have a voltage? It's just a single point. Well, that's where this guy down the bottom comes in. It's the common. The reason we can find a voltage at a node is because it's with respect to the common. The node voltage, or potential difference, is the voltage across whatever's between that node and the common. So for instance here, the voltage Vn is the voltage, the node voltage Vn is the voltage across R2 and R3 here, because it's across from whatever's where the common is. And you can, sometimes they won't put the common in the question, sometimes you'll have to make it yourself, but it doesn't actually really matter where you put it. Usually it's just good to put it in a place where lots of wires are connecting, and we call it 0 volts there. So we mark the common there as being 0 volts. So here's where KCL comes in. We start by taking the currents out of that node that we want to find. So there's currents coming out here, and that's the convention. We always take the currents coming outwards of the node, and then we add them up. This is KCL. We add them up. I1 plus I2 plus I3 is equal to 0, and that's just Kirchhoff's current law. This can be a little confusing at first, what we're about to do, because we're using a current law to find a voltage. So now, using the Ohm's law, we're going to convert each of these three currents into in terms of voltage and resistance. So basically, using this law, we get current is equal to V on R, right? That's just rearranging that. And remember that voltage is a difference between 2 points. So for instance here, when we go Vn to the left, when we go from here to here, it's actually Vn minus Vs. So Vn minus Vs on R1 would be the current coming towards the left out of Vn. And then the one coming down would be Vn, and the voltage down the bottom here is just 0. So it's Vn minus 0, because we've made the common 0 there. So it's Vn minus 0. I'll put it in there just to make everything really clear, and then that's over R2 because it's V on R. These are all just currents. Then we do the next one, very similar to the last one. It's Vn minus 0 again over R3. So you can see, and then we set that to 0 by the current law. And then we can see that these is just one current, the next current, and the other current, and then of course they all equal 0 when we add them up. Alright, so now if we want to find the node voltage, obviously we're going to have to take this equation and rearrange it to find Vn. So this is just basically an exercise in a bit of algebra. When you have two nodes, later on you'll get questions with two nodes, independent current sources and dependent voltage sources. It becomes a bit harder because you've got to use simultaneous equations. But for this one, we've just got to solve for Vn. So first thing I'm going to do is split up that fraction, that first fraction. Oh. Going to split up that first fraction, so it's Vn Vs on R1. And then I'll just won't write in the zeros this time. Just simplifying, I'll bring that Vs on R1 onto the right side, so adding Vs on R1 to both sides. Alright, so now I'm just going to factor out that Vn because it's actually in all of the terms on the left hand side. Alright. And if there's any point throughout this video you feel like, okay, I know where I'm going now, just pause the video, have a go, and see if you get the same thing as I do. Alright, so now I'm going to divide both sides by that big long bracketed term, and you get Vs on R1 outside of 1 on R1 plus 1 on R2 plus 1 on R3. And then I'm probably just going to distribute it out to make it look prettier. R1 over R1 is 1, then it's R1 on R2 plus R1 on R3. So that's probably the best way to express our voltage. I'm sure there's a better way, and I'm sure there's more ways to do that algebra as well. This is just the way I did it. So now we're subbing in those values. We should get these values up here that I've written in. If you sub those in, you should get 6.32 volts. And there's your voltage at that node. That means the voltage across R2 is 6.32 volts with respect to ground, and the voltage across R3 is also the same because they're in parallel. So I might stop that there, and then I'll do another video on 2 nodes.